Okay, good morning. Very few students today. Any reason why? Is there a test or a assignment or something due today? Assignment? Test for which course? CS211? Alright, okay. Okay guys, but nevertheless, I mean, you miss something here, it will affect you as well. Alright. Okay, so I just want to, there's something which we spoke about, finite state machines. Remember we spoke about milli machines and we spoke about more machines, and then I just want to give you one last definition. The last definition which I want to give you is the definition of finite state machines. What is a finite state machines? Well, basically a finite state machine is a machine where the number of possible states is limited. Exactly like what we have been doing in our lectures. All right. Okay. So let's have a look at some of our finite state machines. All right. So let's have a look at this particular state machine. Oh, I'll give you a chance to finish off copying that particular sentence, and then we'll look at the examples. Right? So finite. The word finite means it's a limited number. Yeah. Infinite means unlimited. All right. Okay. All right. So basically, the way I've taught you Wk12-Lec2 is we've done the actual exercises first, and then later on I'm making you realize what is the theory behind it. All right. So I've done what they call a problem-based approach. That's my method of teaching. I'm doing a problem-based approach. We've done the problems. You've done big designs, but you didn't know the definitions. Like for example, only yesterday, like most of you, a few students have already seen me. They've completed their project, right? They've shown their project is working on software. But only yesterday did you come to realize what is the theory and how we build a T flip-flop, how we build a JK flip-flop, and so forth. Yeah? All right? But those students had already completed using those tables. Only yesterday did we find what is the theory behind, what is the derivation behind those tables. So now that data sheet which will be coming in your final exam, right, only now do you realize the theory behind it from yesterday. So same thing goes here. We've been dealing with milli machine, more machine, and we're dealing with finite state machines for a while now, since week 9 or week 8.5, right? But only now do you know that, oh, this is what is called a finite state machine. So all the machines you've been doing so far in your lectures are known as finite state machines. Like, have a look at it over here. This is a finite state machine. Why? Because, why is that a finite state machine? Well, that's a finite state machine because that is 4 states. There's only limited number of states. Yeah? Not flip-flops. We're not counting the number of flip-flops. Well, number of flip-flops is related to number of states because number of states 2 to the power of number of flip-flops gives you number of states. Yeah? Alright? So, yeah, number of states and number of flip-flops is fixed. It's fixed. It's limited. Alright? Okay, so that's a finite state machine here. Okay. That's again another finite state machine. Another finite state machine. Alright. Let's now do a problem on, I'm going to introduce a problem. I want you to start thinking about it. right? I want you to start thinking about it. And then I want to introduce you to a topic called state reduction. In fact, let's do state reduction first. That's slightly longer problem. Then we'll start on the traffic light problem. Just a simple traffic light problem. All right, okay. Because traffic lights is a finite state machine as well. All right. So that was just a simple definition. 3 definitions which you need to know. What is a Mealy machine? What is a Moore machine? What a Mealy machine looks like? What a Moore machine looks like? What is a finite state machine? Right? These are all definitions. Well, Mealy machine and Moore machines come underneath the header of finite state machines. All right? Okay. All right. Now let's do a new topic. It's not a new topic. It's still within our sequential logic design, but we want to. It's a new area of study as far as you guys are concerned. All right. Okay. So there's something called state reduction. Oh, RE reduction and state reduction in assignment. Okay. Okay. Let me just first draw the problem. So you follow me. I'm drawing the problem. Okay. Drawing the problem. So you've got state A, right? You've got state B, state C, state D, state F. Can you see that? Right? State G. So this is the problem. I'm drawing the problem first, and then I'm going to. Okay, so that's going that way, and we say it's going that way, and that's got a 1 0 input 1. So can you tell me what sort of machine is this? Mealy machine or a Moore machine? 1 0. 1 1. Zero zero. I made a mistake. I should have photocopied this picture. Oh, and there's one more, guys. There's one more over here. It's called state E. Zero zero. State E goes up to this guy here again, A, which is 0 0. A loops back in. That's a 0 0. Are you guys able to see this clearly? Or yeah, picture is clear. All right. Okay. This goes back up. That's a 1 1. That's a 1 1 from here. That's a 0 0. 0 0 1 0. All right, there we go. Okay, so how many states in our machine? Oh, well, first definition, is this a finite state machine? Yes, because it has got a limited number of states. A, B, C, D, E, F, G, 1, 2, 3, 4, 5, 6, 7, right? Is that correct? 7 states. Now, if there are 7 states, how many flip-flops do you think are in use? 3 flip-flops. 3 flip-flops should be able to accommodate 7 states, right? So, in terms of bits, how many bit system is this? It's a 3-bit system, right? 3-bit system, 7 states, that means 3 flip-flops. All right. You know, usually we are so used to putting 0, 0, 0, 0, 0, 1 and so forth. In the end, I'm building towards your traffic lights. Remember, right in the first lecture, I mentioned something about traffic lights. Okay? In fact, my plan was to give you a traffic light project, but then everybody would have the same sort of, there's not many different combinations of roads I can give. There's only T-junction and cross-junction, right? Yeah, and if I add pedestrian and all that, becomes too complicated. Some groups will be The T-junction guys will be easy to do and cross-junction will be harder. So I wanted to give something which was consistent to everyone. Alright, now just to let you know, this is another way of drawing it. We can say A is equal to 0, 0, 0, B is equal to 0, 0, 1, C is equal to 0, 1, 0, D is equals to 0, 1, 1, E is equal to 1, 0, 0. All right, okay. E, A, B, C, D, E. Okay, F is equals to 1, 1, 0, G is equals to 1, 1, 1. You guys get the picture now, right? There we go. That's all the loop. Okay. Now, guys, I just want to place this particular information into a state table format. All right? Can we do that? Can we convert this state diagram into a state table? All right? I want you to convert this state diagram into a state table. So let me just quickly put this together. How many of you guys still copying the diagram and the states? Everyone done? All right. Let's now put this into a state table. All right. So I'm going to do a reduced state table, like, you know, just to save space and save time. Do you have a system input over here? By looking at the state diagram, is there a system input? Yes, there is a system input. Is there present state? Yes, present state will have how many lines? How many columns? 3. Right? So on the input side of our state table, there will be 4 lines, right? Then next state. Is there a next state? Yes, there is. How many next states? 3 next states, 3 columns. Is there a system output? Yes, there is a system output. So X and Y, I guess. All right? Okay. So that's your full-on state table, right? And how many, if there is, what do you call, if there is, if there is 4, you've got 1 system input and 3 current states, therefore total of 4. So how many possible combinations? 16. Yeah, 16. So I'm not going to do that. I'm just going to do a reduced one. Reduced meaning just to show you guys based on this. All right. So let's say present state. Present state. Next state with X equals 0 and X equals 1, and system output with X equals 0 and X equals 1. Notice how this is starting to look like, remember when we look at our notes, most of the time the state table is drawn like that. Right? That's a reduced state table. Basically, we're trying to save space because I wanted to put it on the same page. All right? Okay? But in reality, my personal preference is both of them are correct. Whether we draw the state table like this in the reduced way, or we draw it like how we've been doing in our labs, our lectures, you know, the long one with the 16 combinations. That's also correct. But over here, I'm just doing a reduced one just to save space and save time. All right. If our present state is A, B, C, D, E, F, G. All right. Present state is that. If our present state is A and X is 0, what is our next state, guys? Look at your state diagram. All right. Look at your state diagram. What do you get? If present state is A and X is 0, input is 0. A. Okay, let's go. What about B? Let's move downwards this way. Oh, present state is A, X is 1. B. All right. Help me out over here. B will move to C, and if X is 1, D. C, if X is 0, oh guys, I forgot one thing over here. Should be a 1. All right, okay. And there's supposed to be 1 line over here as well. that way. Okay. Now C. If x is 0, come on, help me out, help me out. Let's fill this out, guys. That will be A, right? And this one will be D again. That's D. Let's move to D now. If x is 0, E, and what is this over here? F. Let's move to E, A, F, yeah? F will be G, F, G will be A, F again. Hey, let's do this one. We should have done it all one go, eh? Can you just help me out over here? If Ax is 0, what is the output? 0, yeah? And if x is 1, what is the output? 0, 0, 0, 0, 0. Hey, if I make a mistake, let me know. 0, is this 1? D, we're at D now. D, if x is 1, 1. If E is 0, 1, E. Let's move to E. If x is 0, y is 0. There, 0. And if x is 1, that's 1. F, 0. If x is 1, that's 1. And G, if x is 0, 0. And if x is 1, that gives you 1. Right, there we go. Okay, so remember, the original problem was this. The original problem was this, and this is the reduced state table. You can convert that reduced state table to a large state table like what we do in our notes, right? I'm just saving space just to save time as well, all right? If you want to do the long thing, that would be 16 combinations and take a while. Okay, now, I want to get to the state reduction part. Okay, let me move to the next page if that's all right with you guys. Okay, let's move to the next page. Now the main, the main objective is to reduce the number of states. Basically, to achieve a minimal state diagram. All right. Hey, if you remember, everything we've been doing, remember our conversation from 6-7 weeks ago. Everything we are doing is we are trying to reduce the size of everything. Yeah? We're trying to reduce the size. So for example, and what is the idea of reducing the size? It's cheaper, reduces less space, reduces less energy, easier maintenance. So that's why we were doing Kano maps. If you remember early on, we were doing Kano maps to reduce the size of the particular sum of products function, and we get the minimized sum of products, right? The whole idea. Same thing goes over here. When we do sequential logic design, we've got a large state diagram like that. We want to reduce it, but don't want to reduce the functionality. Right? Remember when we had the sum of products function, the very long one, you put it into the Kano map, and then it gives you the minimized sum of products. But the minimized sum of products and the original sum of products, or product of sums, will give you the same answer. It will behave in the same way. Only that this one, the minimized one, will have fewer number of chips. It's a much more cleaner, smaller system, more efficient, right? Okay? And the other one is a much larger system. So what we want to do is we want to reduce the size. This is too big right now, right? We want to reduce the size and clean that up. Alright, let's show you how to do reduction. That's the word reduction. Another word is minimization. Can you just note down that we want to do system minimization? What we are doing is system minimization. Alright. Okay. Now, what is the key point over here? The key. Okay. The key is if the next state and the key method if the next state and the system output is the same for 2 or more lines, then only we can reduce. All right. Okay. So this is the key method, right? The key technique or method or the key weapon, right? If the next state, right, and the system output is the same for 2 or more lines, we can reduce. I'll show you. Let's go. Let's do the problem now. All right. Now, number 1. I want you to look at, I hope you've got the state diagram and the state table in front of you. Let's look at E. E. Put it in a circle, eh? E is the same as G. How? Let's have a look at it. Okay. E is the same as G. Why? Can you see, if for E, if your input X is 0, it goes to A and output is 0. Let's look for G. If input is 0, it goes to A and the output is 0. So if you apply something, they're both traveling in the same direction with the same output. Yeah? They're both of them, E and G, they're both heading in the same direction and they're both heading in the same direction. Okay, let's look at 1. Eh? If 1 is applied to E, if input is 1, it travels to F, state becomes F, right? And the output is 1. Let's look at G. If 1 is applied to G, the state becomes F and the output is 1. So they are both identical. They do the same moves, exactly the same thing. So that's a redundancy. You see, they're doing the same thing. It's 2 people, 2 states doing exactly the same job. All right. So let me just list it down here. E goes to A if it's 0, 0, and E goes to F if it's 1, 1. On the other hand, G goes to A if it's 0, 0. If it's 0, then output is 0. And G goes to F if input 1 and output will also be 1. So can you see they are identical? They're doing the same thing. The output is the same. Therefore, we can confidently say that E is equal to G. Right? So therefore, what do? We eliminate G. We eliminate G. Alright, so let's come back to our original question over here. We eliminate G. So let's try and do that. So I'm going to eliminate G. So there. This guy is gone. Oh, you choose. Which one do you want to eliminate? Eh? If you want, we can choose. We can either eliminate A or G. Eh? Because, E is equal to G. Oh, we can either eliminate E or G. So I choose to eliminate. We eliminate one of them. All right? Eliminate one of them. Set. You see what I'm doing over here? All right, now let's move to the next guy. Number 2. Number 2. Number 2. Let's look at any other case, guys. I want you to identify. I give you a chance. There we go. If you get a question in the exam, you should be able to identify. Any other replication? You can look at the table. The table and the state diagram are the same thing. Just drawn in different ways. Some people find it easier to identify replication in the state table. Some people find it easier to identify replication in the state diagram. I think I found one. Okay, let me mention this. Okay, let's continue. Otherwise, we won't finish. I want to finish this problem today. It's a slightly longer problem, but I'm taking it slow. Now, remember, since E is equal to G, G is replaced with E, or another way of saying it is, or E is replaced with G, whichever is convenient. Which is convenient to obtain a result. Now let's look at D. Look at D. Let's look at D. D goes to F, and E is also going to F. Okay, so let's write it down. With D, if the input is 0, I'm looking at my state diagram. If the input is 0, it goes to E, and the output is 0. If for D, if the input is 1, it goes to F, and the output is 1. On the other hand, I want you to look at F as well. F. If the input is 0, it goes to G and output is 0. And if input is 1, it goes to F, it goes to itself, and output is 1. What can we say therefore? Therefore, we know that F is equal to D. So we choose to eliminate F. Set. You saw what I did over here? I want you to follow, have a look at this over here and see what I did over here. All right, I've just written that thing down. Eliminate F. Give you a chance to have a look on your thing there. So D, when it's 0, D becomes E and output is 0. When D, if it's 1, state becomes F and output is 1. Let's look at F. F, if it's 0, sorry, what were we comparing? D and F. Yeah. F, if it's 0, output is G, and if it's 1, it remains at F. Right? Now, remember something over here. I've missed something over here. Guys, what do you recall now at this point? G, in our last move, what did G become? G has become E now. Right? So just put in our last move or reduction, G became E. Yeah? All right. So people will say, hey, these two are not the same. Well, we just realized that G and E are the same thing. We removed. Yeah? Okay, so that's the missing part. Everyone with me? Anybody got a question? There's only a few of you. So any questions? Let me know. All right. So it's fairly straightforward right now. So A, we're doing eliminate F. So let's come here. Eliminate F, gone. So I've taken F out of the original thing. Now our final state table. Our final state table will look like this. So our state diagram. So state table will look something like this. We've got our present state, our next state, output, okay, A, B, C, D, E. What happened to G and F? Gone, they're missing, eh? All right. So now we just copy from our original problem paper. We copy from our original problem paper, original question paper. That will be still be A, C, A, E, A, A, C, A, E, A, B, D, D, but what can you tell me about F, guys? F has now become D. All right, F has now become D. Remember, there was two F's over here. Last two F's, they have become D now. Okay? All right. Now, we now draw our state diagram. Oh, I give you a chance. So based on our new thing, we draw a state diagram. How about I just draw it on the side over here? Okay, it's a smaller diagram now. So maybe save some space there. Okay, so we've got A, B, C, D, E. All right, and we have 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, so that's our final reduced state diagram. This is our reduced state diagram, also called minimized. All right, winner, winner, chicken dinner. All right. Okay. All right. So have a look. I want you to compare this reduced diagram with the original diagram. Look at the original diagram and look at the reduced one. So the whole point is, you remember, our design is, we want to reduce as much as possible. Now a good question is, would you be able to do reduction in your state diagram? Check that out. Okay? In your project. Are you able to do reduction? Because obviously the larger the state diagram, the more the states, the more of a spider's web which you have to deal with in terms of your state table, the transitions, all these things, right? But if it's smaller and a cleaner state diagram, you have much more easier access. Yeah? You get what I'm saying? All right. Okay. Any questions, guys? Let me just start off with traffic lights. This is just an application problem. Let's talk about traffic lights. That's a simple traffic light. I'll do a simple one today. We won't solve the entire problem. We won't draw the circuit and all that. I'm just going to draw, you know, how we control one set of traffic lights. So let us say we have a set of traffic lights. What comes on top, guys? Is it red? Red is on top? Red, orange, and then green, right? In the sequence. Okay, so red. Let's say this is green. So red. Oh, traffic lights. Basic. Red. Let's say this is green. It's green, eh? Anybody got a green pen? No? Okay. And let's say this is orange, eh? Okay. All right. So let's just try and deal with how we can handle the lighting of this particular traffic system. Now, sequence. Let's think about the sequence. Let's think about the sequence. So the first sequence is, if we say red, orange, OR, eh? Red, orange, green. When red is on, it will be on. These two will be off. Yeah, simple. Then after that guy, after that, what is the next sequence? Right? It will be green. Right? Then it will be orange. Okay. But this table does not give us much information. That's why we don't go to the table straight away. Let's now try and deal with it in terms of our state diagram. So over here, problem. Problem is that very confusing to do design, right, based on the table. So not a good idea. Not a good idea to start off with that. All right. So no, I'm deliberately placing that note there so that students don't make that mistake when they're doing design. The best place to start off design is from our state diagram. So we have red, we have green, we have orange. So red, green, orange. Now, after a sufficient time has passed, red becomes, right, while it is red, there is a particular timing. It stays at red for a while. Yeah? It stays at red for, let's say, how many seconds? Can you give me an estimate? Let's make it small. 60 seconds for red? Right, 60 seconds, let's say we're just doing a 1, yeah? Okay, so it stays here at 0, no movement, right? The input is 0, the input which triggers the trigger. Trigger is equal to 0, the input trigger is equal to 0, and it stays here, right, at red. Okay? Now, once it gets triggered, and the trigger stays here for how many? for length of 60 seconds. Now from red, it will move to green. After 60 is up, oh, yeah. For 60 seconds, the trigger remains at 0, right? Once trigger becomes 1, right, it moves to green, yeah? And then it stays green for how many seconds? Let's say, okay, let's keep it at another 60 seconds. 0 for 60 seconds. Then from green, it stays at 60 seconds for green, 60 loops, yeah? So in your table is the same thing, 60 loops, right? Now from here, it goes to orange, right? If it's 1. Now it stays at orange, not too long, eh? Doesn't say 60 seconds. Let's say how many seconds it's orange? 10. Yeah? Okay, so it's 0, the trigger is 0 for 10 seconds. The moment the trigger becomes 1, something says, okay, next state, right? Okay, the trigger, right? Then only it will move to here. So can you see the loop for that particular traffic light? Now, how do we build this trigger? How do we build this trigger? Well, how would we do 60 seconds? Let's say the number 60. The number 60 is how many bits occupies the number 60? How many bits occupies the numbers? How many, if you want to do 60, the number 60 in binary, how many bits is that? 2 to the power of, okay, let's do it like this. 2 to the power of 3 is, number 8 is 2 to the power of 3. 16 is 2 to the power of 4, right? 32 is 2 to the power of 5. 64 is 2 to the power of 6. So in order to accommodate the number 60, we've got to have 6 bits. So we now build a 6-bit flip-flop system. We're talking only about the timer over here, okay? The timer. How do we build the timer for 60 seconds? Right? Now 60 seconds is 6 bits. Yeah? 60 seconds would take up 6 bits. And, or is it 5 bits? No, the number 32 is 5 bits. Yeah, 5 bits. 5 bits. Right? Number 63, all the way till number 63, it occupies 5 bits. The number 64 will occupy how many? 6 bits. Right? Number 128 will occupy, yeah, alright. Okay. So, then what we do is, we place, you guys built counters, remember that? Yeah, you built a sequential counter. So we build a counter which counts from 0 to 60.